Hello everyone. Through this video, we are going to discuss about the basic subcircuit designs in LTSpice. So firstly, let me explain basic blocks. So which are logic gates, amplifier and comparators. Under the logic gates, we are going to discuss inverter, NOR gate, NAND gate. Then finally, we will discuss the SR latch, JK flip-flops and counter, up and down counter, binary shifters. There are many things actually. So under the amplifier, today we are going to discuss about the second stage amplifier having the PMOS differential input. Finally, I will explain how to convert amplifier into the comparator. Firstly, the logic gate. So under the logic gate, inverter. Similarly, we can call NOT gate. Okay. So here is the schematic of the NOT gate. So now let me draw the schematic using LTSpice. These are the symbol and schematic because I have already created the symbol and the schematic. So now let me explain. To design the NOT gate, I have to select PMOS and NMOS. So here is the PMOS and then I have to select NMOS. So here is the NMOS. So after that, I have to connect. So here is the gate connection and this is the source of the PMOS and this is the source of the NMOS. So this is the body connection. Body should be VDD for the PMOS. Body should be ground for the NMOS. So then I have to select the WL ratio. So to select the WL ratio, I just need to right click on the PMOS. So then it will give this window. So then now I can select WL ratio. So let me select 300 nano for the channel length and 1 micro for the width. Here, similar, 300 nanometer for the length, 500 for the width. So most of people, they select the width for the PMOS, which is 2 times compared to the width of the NMOS. So let me add 1 micrometer for the PMOS. So previously I already added 500 nanometer for the width of the NMOS. So now I have to create pins. So to create the pin, I just need to press Enter. So here it will give this window. So then I'm going to add the pins. VSS, and I have to select the bidirection, then click. So here's the VSS, and again bidirection, VDD, and again maybe A, which is input, and B, which is output. Okay. So now I have added 4 pins. 2 are supply voltage, A is input and B is output. So now I have to create the symbol for this inverter. So here is the way. So we need to go to the hierarchy. Under that hierarchy, you need to open first one. So open this seed symbol here. Then it asks, couldn't find the seed symbol. Shall I try to automatically generate one? Okay, then yes. So here is the symbol. But as we know, inverter has its own structure, okay, similar to what I am drawing, okay. So let's press the L. Here and again the circle. Now I'm going to move this label. So B is the output. So A is the input. VDD, VSS. So now I can delete, okay, this thing. So here's the symbol. Then you have to save this symbol. Folder, component, then inverter. Done. So let me close this one. So here's the symbol. So let me save this one also. Similar to the component. This is inverter. Okay. So now I can close this one also. So now I'm going to simulate that inverter. So let me show you. Because I need to open the schematic environment. So here's the schematic environment. Then I have to select that inverter. So you just need to go to the components. So in that components, you will see here the direction. So in it has inverter. See, here's the inverter. Okay. Okay. So we supply. Now I have to select the voltage source. Here's the voltage source. And also I have to select some pulse generator. The special thing is I have to add the ground. Okay, here is the ground. So press G is the ground. So then connect, and also connect here. So now this is the input, which is pulse signal. Okay, so advance. This is the pulse. So T on time, 2 volt, delay, no delay, reon, when the micro, period, 40 micro, and then okay. Here, this is just the DC power supply. So maybe 2 volt. Okay. no resistor, 0. Okay. Then I'm going to configure the analysis. So here's this time. Okay. So 100 micro. Now I can run the simulation. Okay, let me show you. This is the input signal. So this is wave, and this is the inverting signal. So you can see that. So it has some delay due to some parasitic capacitors. So it's correct. Okay, the output should be the inverse of the input. Okay, which is correct. Okay. So now we can go for the NAND gate. NAND gate is very simple circuit which has two PMOS and two NMOS. So this is the schematic of the NAND gate. Okay, these are the schematic I have created using the LTSpice, and this is the related symbol. Okay, so now we can go for the simulation. So here is the schematic of the two input NAND gate. So I have already designed whole structure of the NAND gate. Okay, which means I have already added the supply inputs and also the signal inputs and output. Also, I have selected the WL ratio. This is very similar to the inverter. You can add the pin. You can just press the N. Then by using this the small window, you can add the pin. Okay, but make sure that the input VDDVS should be bidirectional. Okay, and if you want to change the WL ratio, that just right click on the any MOSFET, PMOS or NMOS, then it will give this window to change the W ratio. Okay, very simple. So once we have already created the whole schematic, including the pins, we can generate the symbol. To generate the symbol, we need to go to the hierarchy. Under the hierarchy, you can see that open this sheet symbol. Okay, just click. So here is the symbol. Since I have already created symbol also, so I don't need to create anymore. Okay, so maybe you have to create by yourself. Okay, you can just press the L, so then you can draw whatever you want. So then you can move this notation onto your symbol, then save it. Okay, very easy. So let me close this one. So now, and now I'm going to simulate this NAND gate. Okay, so here is the schematic for the simulation. So as I mentioned, I already created the symbol, and then I have connected the supply voltage, which is 2, and also here is the pulse signal, and this is just the constant voltage. Okay, this is just the constant voltage, which is 2 volt. Okay, so according to the truth table of the NAND gate, the output of NAND gate should be 0 when the 2 input becomes 1. Output of the NAND gate should be 0 when the input A and B become 1. So you can see that, see, here is the signal A and B. Okay, so just for the B, I have given the direct volt 2 volt, and for A, I just gave the some pulse signal. Okay, so you can see that now here is the two signals similar to the 2 volt. Okay, so there the output of the NAND gate becomes 0, which means this is working. Okay, this is working. Third one is the OR gate, similar to the inverter and the NAND gate. So this is the NOR gate. Okay, NOR gate also has 2 PMOS connected in series. Then the 2 NMOS that should be connected in parallel. Okay, these are the schematic and symbol respectively I have designed using the LTSpice. Okay, now we can go for the simulation. So here is the NOR gate. Okay, so NOR gate also very similar to the NAND gate. Only different is, so PMOS previously we have connected in parallel for the NOT gate, but for the NOR gate we have to connect the PMOS in series. Then and the NMOS should be connected in parallel. Okay, that is only difference. For this also, I have added the every pins including VDD, VS, AB and F, and also I have selected the WR ratio. See, I have already selected. So now I have to design the, I have to create the symbol. Symbol also I already created, but let me show you. So then just go to the hierarchy, then you will see this. If you have already created, then you will see this symbol. Otherwise, you have to create it. Okay. During the creation of the inverter, I have already explained. Okay, so then you can follow that. Then close. And this one also let me close. So here is the schematic for the simulation. So, and here also I have added. See, this is the input which is 0 for the B, and for the A, I have added the pulse signal. Okay. So then what will be the output? So here is the output. So let me close this one first and run again. Okay. For this one, I'm going to get the output signal. For this one, I'm going to get the input. Here also input. See. Now you can see that. For the NOR gate, what should happen? Only when the input become 0, the output should be 1. So this is the condition for the NOR gate. Again, only when all input becomes 0, then output becomes 1. So let's see. Here is the 0. And this is the other input signal 0. So both are 0, the output become 1. Otherwise, it is 0. So here, let me add the another pulse signal, then it will be very clear. Okay. So pulse signal 2 volt and on time maybe 10 micro, and the time period similar 40. Okay, which is similar to the input. Now close and simulate and separate into 3. This is for the output. This is for the one input, and this is for the other input. See, now you can clearly see that only when the 2 input becomes 0, see, in here also 0, here also 0, then the output of the NOR gate becomes 1. So otherwise it is 0. Okay, so which means that the NOR gate also perfectly working. So now I'm going to explain about the amplifier, which is little different from the logic gates actually, because amplifier we are mostly using for the analog circuit. So in that case, we have to run the different kind of simulation. Maybe you already know that. This is the basic symbol of the amplifier. Okay, basically amplifier has 2 input, which are inverting and inverting, and also the supply voltage and the output. But when it comes to reality, there should be another input. Sometimes that input related to the voltage reference, or sometimes that input related to the current reference. Okay, so we need to control the voltage and current inside in order to bias the amplifier. So these are the basic things that we should know of the amplifiers. The open loop gain. So theoretically, which is infinity. So, but the practically, sometimes 60 dB or 8 dB. Some amplifier can achieve 8 dB mean good, very high gain. Okay. Second, input impedance. Theoretically, which is infinite. So the impedance across the inverting and non-inverting, or impedance across the inverting compared to the, respect to the ground, or non-inverting respect to the ground. All are infinity. But in theoretically, it has very high impedance like a 100 mega ohm. Okay. Third one, output impedance. In theory, which is 0, but sometimes it is some few ohms. Okay. So final one, fourth one, offset. Similar to the previous condition. So the offset should be 0. When we go for the theoretical analysis, we can easily assume that 0. But when it comes to practical, when it comes to reality, which is few millivolt. Okay. Here is the schematic of the amplifier. So as I mentioned at the beginning, so this amplifier, we can say that two stages amplifier, which means it has two differential pair with one output, which is the first stage. Then this is the second stage. So altogether, we can say that this is second stage amplifier. And also, this amplifier consists of PMOS differential pairs. PMOS differential pairs. So the benefit, the advantage of PMOS differential input pair is this amplifier can handle, this amplifier can control, this amplifier can amplify relatively small voltages compared to the similar amplifier having the NMOS differential pairs. Okay, see, PMOS differential pairs. And here is the current biasing. So we have to select current source or suitable resistor for the current biasing. Okay. And this is the amplifier structure, but in here it has already two inverters connected in series. Then it has connected the output of the amplifier. This is just buffer. Okay, buffer. It doesn't change the signal. Okay, I mean when this become 1, this is 0, this is 1. Okay, 0 0 doesn't change the input. But when we add this kind of two inverter with the amplifier, we can easily convert the amplifier into the comparator. See, very easy. Only difference is we have to use two inverter. So normally two inverter we can say as buffer. Okay. So this is the LTSpice simulation. Finally, we can go for the simulation in the LTSpice. Okay. So let me show you. So before go that, here is the preference, because during this lecture, during this video, I'm not going to explain how to calculate this WL ratio. So to calculate the WL ratio, very complicated compared to the logic gate. Okay, logic gate, we just need to select minimum WL ratio, okay, to handle the current. Okay, but in the amplifier, like the analog, for the analog circuit, we have to calculate the each WL ratio. These are different. So you can see that 25 divided by 1, 30 divided by 1, 30 divided by 1, 30 divided by 4, 10 divided by 4. Those are different, which means that we have to calculate this one. So we have to calculate, and after that, while we obtaining the simulation, we have to optimize this value by fine tuning. Okay. So here is the schematic of the operational amplifier. You can see that it has two differential inputs and one pin for current biasing and output, and then VDD and VSS. I just use the comparator that I have already used in my research paper. Okay, so I already designed this comparator. So I just copy paste from the, I just copy paste of the each WL ratio, okay, from that paper. So you can see that in here it has 1 L and 25 width. In here you can see that it is 30 width and 1 micro is difference. Okay, so in here see 4 micro for length, 20 micro for width, are different actually. So see, This is not similar. These are not similar. So see, for micro, 10 micro for the width, it's not similar. So I have already calculated the each W ratio using actually many equations. First, I have to define the gain and I have to assume some current. Then I need to write some equation. Every MOSFET should be at saturation region. I have to consider many theory and conditions. And also I have to assume several things. So, okay. So I will explain those things later, okay? You can create the symbol. After creating the symbol, you can go for the simulation. So here is the simulation schematic. So in here, I'm going to run the gain simulation. See, I have already run the gain simulation. So let me run again. So first I need to close. In here, this is the biasing current, okay? So biasing current. So I gave the 40 micro. So this is supply voltage, 2 volt. And this is 0.8 means this is common mode voltage, okay? Common mode voltage, which means that this 0.8 I have given for these two inverting and non-inverting inputs. This is common for these two inputs, okay? And here is the small signal source, how I made that one. So you can see that here would be none, and here AC amplitude, the small signal AC analysis. See, you just need to add some signal. Okay, then okay. After that, you have to go to the configure analysis, then have to select the AC analysis. Under the AC analysis, I just select the decade and the number of 0.20, the frequency variation 1 to the 100 mega ohm. Okay, 1 hertz to 100 mega ohm. Then okay. Finally, hit the run button and select the output. See, you will see very beautiful waveform. And here is the gain waveform as the function of the frequency. This is the phase margin. This is the phase as the function of frequency, which means that this amplifier is now perfectly working. See, you can see the gain. This is quite high gain, okay? Quite high gain. This is good amplifier. Let me explain the comparator by using this amplifier, okay? So, you know the structure of the amplifier. So, here is the amplifier, okay? If you want to design the comparator, which is very easy, you just need to add 2 invert with the output, okay? Let me delete this one. Let me delete these two also. And I'm going to add the inverters, okay? Okay. So now here is the output, okay? Here is the output. So now I'm going to add some sine wave to compare. So voltage. So here is the voltage. So let me delete this thing. So in here, sine wave, okay? Sine wave. Amplitude 1 volt, maybe 2 volt. Frequency 10 kilohertz. Okay. And here, for the inverting input, I'm just going to add another power source. For the source, now I am giving 1 volt, okay? Just 1 volt DC. And I have to delete this simulation and I'm going to run the transient analysis. Transient analysis. So here is the time. Done and run. So these are the inputs. So you can see the sine input and the constant voltage, which is known as reference. So then what will be the output? See? So let me increase the time interval. Then it, okay. In here for the input, here for the input, and this one for the output. See? Okay. See? This is the function of the comparator. So what is the function? So I have added sine wave for the non-inverting input. So this is the non-inverting. So this is the inverting. So what is the condition of the comparator? When the non-inverting input become higher than the inverting input, comparator output will be high. So this is the high. Otherwise, comparator output will be low. So this is the low. So you can see that when I decrease this value, maybe down to the 0.4. So you will see the down to 0.4 means in here, okay? So now it's this 6.4. Maybe I can reduce this value, maybe 0.1. See? So the summary. We have already discussed about the inverter and also OR gate, NAND gate, comparator. Before the comparator, we discussed the amplifier, okay? So during my next lecture, let me explain the several sub-circuits. Sub-circuit means I'm gonna combine two comparators and some logic gates with some resistor and capacitors. So then it will give the sub-circuits. So PDC, DAC, some current mirror circuit, oscillators, those are the example for the sub-circuit. Okay, so see you next time. Thank you.